Okay, so when you're trying to find the Thevenin equivalent of a circuit, essentially what you're doing is you're taking a complex circuit like this and you're converting it into just a voltage source with a value of V Thevenin connected in series with a resistor of value R Thevenin. And of course you have these two output terminals with your output voltage there. And from an outside perspective, whatever you connect to these outside terminals will be the same as if you connected it to the original circuit. And we can do that because all our components that we're dealing with here are linear. Alrighty, so there are a couple methods of going about this. For finding V Thevenin, or Thevenin voltage, what you want to do is find the open circuit voltage across the terminals. Open circuit means that you're just looking at the voltage difference between these 2 points with no components in between. It's open here. So there's no current flowing. You're just looking at the voltage here minus the voltage at the bottom. And that is your V Thevenin, which will then go here. And then for RTH, your Thevenin resistance, there are a couple methods that we will cover. So the first one that we're going to do here is network simplification. And this involves just combining, or first of all, you deactivate your sources. In this case, we only deactivate our independent sources. You never want to deactivate dependent sources. And then simplify parallel and series resistors. And you just keep doing that between these two terminals until you have just a single resistor. And that is your RTH. So this only works, however, if you have no dependent sources. So if there are any dependent sources within your circuit, that means you won't be able to deactivate them, and you won't be able to simplify it to just one resistor. So in that case, we go to the short circuit current method. In this case, you don't deactivate any of your sources, and all you do is short the outputs or output terminals and find the current across it. So in this case, that would mean drawing a wire between these two terminals, solving the circuit as it is, don't deactivate any of the sources, and then finding the current right here that's flowing through that. And because of Ohm's law, we already found the voltage. So V equals IR. We know that RTH is going to be equal to our voltage, Thevenin voltage, divided by the short circuit current. Alrighty. And then the third method, oh, no, there's one more thing. There are additional situations where you won't be able to use short circuit current for this. If there are no independent sources, or rather, no output voltage. If there's no voltage between your outputs to begin with, then you know there isn't going to be a current going through there. So then you won't be able to use that zero current to find RTH, because 0 divided by 0 is undefined. So we're going to move on to the third method in case you're trying to find a circuit with dependent sources and without an output voltage. In this case, use external source method. So this involves deactivating the independent sources, applying a test voltage or current to your circuit. That would look like, so we deactivate all these, this would become open, this would become a short, and then across our output terminals we apply either a current or a voltage. It doesn't really matter, just whichever you think will go faster. And then you find the current voltage across that. And using this method always works, as long as your circuit is linear. So as a recap, network simplification, simplest method, but if you have dependent sources, it's a no-go. Short circuit method, it's a little more complicated than resistor simplification, but you can use it with dependent sources, but you need an output voltage. If there's no output voltage, then it's a no-go. And finally, external source method, probably the most complex, but it always works. So I'm going to go and do a couple examples of these. Okay, so starting off with this first circuit, we're going to first find Thevenin, so that's our open circuit voltage. And to do that, I'm just going to use node voltage analysis. So I'm going to identify all our extraordinary nodes. I'm going to label this one as ground. And then I'm going to start writing some equations. So we have, starting with V1 up here, I'm going to do V1 minus 8 over 4 plus, that's 1 amp going out of there, and V1 minus V2 over 2 all equal to 0. And for our V2, we just have V2 minus V1 over 2 and V2 minus V3 over 4. And that's everything, because we do not have a current going out this way. There is nowhere for it to go, so we only have 2 currents in our equation. And then finally for V3, we're going to start with this current source. Again, for node voltage, we do the current exiting So that's in the opposite direction. So we put a -1. Then it'd be V3 minus V2 over 4 plus V3 over 2 plus V3 over 4, because both these are going to ground. And all equals 0. Let's go ahead and solve the system. We have 3 equations, 4 values. I'll go ahead and input all these. And we're going to put that in row reduced form to get our final answers. So we have V1 at the top, V2 at the middle, V3 at the bottom. Which one do we want? We are looking for V2 because our output, Thevenin right here, is equal to the voltage at this point because there's no current flowing. There's no current flowing means there's no voltage drop. So this is also equal to V2. V2 minus 0 equals V2. So finally our Thevenin is the second term in this matrix over here. 2.588 volts. Okay, and now to find our Thevenin. So what we're going to do this is we're going to deactivate our sources. So current source becomes open circuit, voltage source becomes short circuit. And now we're just going to combine in series and parallel. So let's look for our series and parallel combinations. These two resistors are in series, so I'm going to combine them to just 6 ohms, like that. These two are in parallel, right here, are in parallel. So I'm going to combine, I'm going to combine them to, let's see, what would it be? It was 2 and a 4. So that is 4/3 ohms. That is in parallel with this one right here. So we're going to add 4 to that. Oh, too much. So again, that was 5.3. These two are now in parallel, sharing the same 2 nodes. So I'm going to do that real quick. That's a nasty number, but they combine to just one resistor of value 2.8. And then we add that to 2 to get our final Thevenin resistance of 4.82. 824. Okay, so that is our problem solved right there. And if we want, we can go ahead and write out our little Thevenin equivalent circuit. So we have our voltage source and our resistor and our VTH and our RTH. Alrighty. So in this next example, you'll see that we have a new dependent source over here. So if you'll remember, that now excludes us from using our simple resistor simplification. We now are going to use the short circuit current method to find our Thevenin resistance. But first, of course, we want to find our voltage. So this one, I don't think we have to use node voltage analysis, because if you'll see, we know that this point right here is 20 volts, and then we essentially have two resistors in series, which is a voltage divider. There's no current going this way, so we don't have to worry about this. This is essentially a voltage divider right here. And we want to find the voltage at this point, because since there's no current flowing through here, that will be the same as the voltage at Vx that we want. So let's go ahead and do that. We have, we'll label it Vx right here. Vx is equal to 20 times the voltage across the resistor that we want to measure. That is 30 ohms, or sorry, the resistance of the resistor we want to measure, divided by the total resistance of the series. So that is 10 plus 30. So it's 20 times 30 divided by 40, or 3/4, and that is 60/4, or 15. Okay, and that is volts. So Vx is equal to 15 volts. Now we can go over to this part and write a quick KCL equation for this. Let's see, we have, actually, let's just combine these two. That'll make things easier. We have a 20 and a 50 in parallel. That combines to 14.3. And our voltage here will be equal to our current times the resistance right here. So that is 3 Vx times 14.3. I'll go ahead and do that. 3 times 15 times 14.3. That is a lot of volts. Okay. 642.86. So this is quite the amplifier here, and that is volts, or V Thevenin. So now we want to find the Thevenin resistance by shorting our output and then finding the current through it. In this case, that's pretty easy because we have a current source right here. And all the current from that current source will now be diverted to the short. So the current through that is equal to 3 Vx, or as we found, 45 amps, which is a lot. Okay, so we now multiply that current. No, we don't multiply. To find our Thevenin resistance from Ohm's law, we take our Thevenin voltage and divide by the short circuit current. I'll put that there. ISC. So that is 642.86 divided by 45, which is 14.28. So yeah, the same resistance we had here. Alrighty. And it isn't quite necessary, but it's always good to write out our little Thevenin equivalent circuit. The 642.86 volts and the 14.28 ohms. Okay, with this final circuit, you'll notice that we no longer have any independent sources. We just have two dependent sources. So when this circuit is just left alone, nothing will happen. This will be, these won't have a Vx to go off of, it'll just be zero. Everything will have no current, everything will just be zero. So we have no output voltage. And from that, we know we can no longer use the short circuit method. So we're going to be using the external source method. And of course, for this one, we already know VTH equals 0. So we're just going to be finding the equivalent resistance. However, we cannot just simplify it because of these dependent sources. So we're going to have to attach an external source. So what that looks like, we're going to go like this to our output terminals. This can either be a current source or a voltage source, whichever you think will be faster. You'll get the same answer in the end. But looking at this, it looks like it might be useful to have a constant Vx in this circuit. So I'm going to make this a voltage source. It's always just 1 volt or 1 amp. And now I know that Vx is equal to 1 volt. So now I can go through and I know that this is now just half volt. And this is now just 1/4 of an amp. So now all I have to do is find the current going through here. We'll call it IS. To do that, I think I'll use node voltage analysis. So let's look at all the nodes we don't know. We know this is an extraordinary node, but since we'll go ahead and label this ground, we know that ground up 1 volt is just 1 volt. So we know this. This dependent source is going off of Vx. So 1/2 Vx is just one half a volt. So from ground up 1/2 a volt, we know this point is just 1/2 of a volt. And it looks like the only unknowns here are this node right here and this node right here. We'll call it V1 and V2. So we're going to make our equations real quick. Starting with V1, we'll go V1 minus 1 over 16 plus the 1/4 of an amp because it's exiting, plus V1 minus V2 over 16. All that equal to 0. For V2, we'll go V2 minus V1 over 16 plus V2 minus 1/2, because it's going to that center node, divide by 16. And finally, V2 minus 0 over 16, because it's also going to ground. Okay, now I'm going to go ahead and input these into our matrix. We've got 2 equations, 3 terms. And we'll go ahead and put this in reference form. We find that V1 is negative 1.7 volts and V2 is negative 0.4. So how does that help us? We're trying to find current. Well, let's see. To find the current leaving here, leaving this source, we want to add up this current, and this current. So writing a KCL equation for that, we'd say IS is equal to this first current, 1 volt minus 0 over 16. Second current here, 1 volt minus 0.5 volts over 16. And this third current that goes to V1, we have 1 minus negative, so it's plus 1.7 volts over 16. So we add all these together. 1 by 16. And we get 0.2625 amps. Since we know the voltage is 1 volt, we know our Thevenin from Ohm's law is just 1 volt divided by the 0.2625 amps. So our Thevenin resistance is 3.81 ohms. So if you were to rewrite the circuit, it would have a voltage of 0, and then a single resistor with 3.81 ohms. And of course, you can just get rid of that voltage since it doesn't really mean anything. Alrighty, that's that.